Hello, good morning, respected audience. My name is Salman Parvez. I am Associate Professor of Mechanics. I will be discussing the current prospects and challenges of multi-jet fusion technology. So, before going further, what is meant by multi-jet fusion technology? Multi-jet fusion technology is an additive manufacturing technology which was commercially released in 2016 by HP. It consists of an inkjet array of fusing and detailing agents that are applied across a bed of powdered material layer by layer. These layers are fused together simultaneously by a heating element, producing a solid part. As far as the motivation is concerned, despite being introduced just few years back, multi-jet fusion has gained the reputation as a major competitor to SLS. Which is the third most common 3D printing technique after stereolithography and fused deposition modeling. Multi-jet fusion technology is unique in its function, which allows for low manufacturing times, competitive part properties, and minimal post-production finishing, which are all desirable for various industrial applications. A brief idea about the working mechanism of multi-jet fusion 3D printing is shown in this slide. Multi-jet fusion 3D printer consists of a build platform, power supply, infrared lamp, fusing, and detailing agents. Infrared lamps emit energy over the powder bed during each layer coat. The layer times are constant and not dependent on the cross section of the layer, thus giving faster layer times irrespective of layer geometry. Fusing agent is applied selectively over the powder bed. That is, within the model boundaries, it contains carbon black, which helps improve absorption of the infrared energy and also has an effect on the mechanical properties of the part. After that, the detailing agent is applied along the contours of the printed parts to prevent melting of the powder, which is in contact with the fusing material, thus providing sharper details and improving dimensional accuracy. Uncentered powder is reintroduced to the powder cycle. About 20% of virgin material is mixed with recycled powder, thus ensuring least wastage of material. Currently, there are different compatible materials, but the most common one is PA12, PA12 with glass bead, PA11, and the other ones as well. In the section of current performance, first I'm going to discuss the feedstock and the print characteristics. So the HPPA12 powder is the material majorly used in the MJF printing. It shows nearly spherical morphologies and smooth surfaces. This ensures good flowability of powder feeding and increased accuracy of the printed parts. The powder particle size falls in the range of 45 to 90 micron, which is considered a good particle size for powder bed fusion processes. Recycled materials, molecular structure, and melting temperature does not show any significant difference when compared to the virgin material. Printed parts deposit partially melted PA12 powder particles on the surface, which can be removed by post-processing methods recommended by HP. The chemical and thermal properties. Multi-jet fusion printed parts made of PA12 and PA12 with glass beads have thermograms with a single broad endotherm centered around 183 to 186 degrees Celsius. This suggests complete powder sintering during multi-jet fusion printing. With respect to the chemical properties, it is found that major elemental concentrations obtained for PA12 parts are carbon and oxygen, and there are some other elements as shown in the slide. As far as the mechanical properties are concerned, literature shows that tensile strength increases in the order from x-axis, y-axis, and z-axis build orientation for multi-jet fusion printed parts. However, average tensile strength in all directions is higher than similar processes using similar materials. Z direction shows high tensile strength and lowest percentage elongation at break. This is due to possible additional weight of the layers in the Z direction, which forms a denser and less porous part. Flexural strength of multi-jet fusion printed parts increases in X, Y, and Z directions orderly, which is influenced by the porosity of the parts. Multi-jet fusion parts exhibit a ductile deformation at the fracture interface. The level of ductility observed is higher than any other similar powder bed fusion process. This behavior of multi-jet fusion parts provides them with high energy absorption before failure, which leads to high toughness of the parts. As far as the surface quality and dimensional accuracy is concerned, industrial applications require high dimensional accuracy, especially when it comes to functional parts and prototypes. Parts generally exhibit varied surface roughness at the top and bottom surface of the part. Journal findings show rougher top surface and smoother bottom surface. The smoother surface at the bottom could be due to the detailing agent, which is possibly applied in the bottom layer. In the case of Z direction, better centering of the bottom layer could justify the smoothness. Multi-jet fusion parts show small profile deviations. A complicated design of a Marlin using multi-jet fusion technology showed profile deviations ranging from 1.1344 mm to 0.668 mm. Multi-jet fusion parts show a slight curvature on the top surface and at the contour edge of the solidification. This could be due to the presence of surfactants in the agents used, which results in change of wetting condition at the outer edge of the part, thereby leading to distortion of the liquid meniscus, distortions of edges. Recent studies are trying to understand this effect and find solutions for it. Multi-jet fusion technology comparison to SLS. SLS has a slower processing speed than MJF since the laser sinters the powder point by point, unlike MJF, which follows a line-by-line approach. Currently, MJF does not provide enough flexibility when it comes to setting different process parameters for printing, unlike SLS. For SLS process, the PA12 powders show a presence of cracks, which are not that evident in MJF powders. The parts printed by SLS have a higher porosity percentage than MJF printed parts. In a study, porosity of SLS and MJF blocks printed in the same direction were 5.72% and 5.07% respectively. When it comes to the thermal properties, both show similar characteristics. MJF parts show slightly higher tensile strength and flexural strength. SLS parts show a brittle failure and are much stiffer than MJF parts. SLS parts made out of aged powder show a dramatic decrease in its mechanical performance, whereas no significant degradation was seen in MJF parts. Some major conclusions are as below. The MJF printing has become a promising additive manufacturing technology because of high build rate, consistent material performance, and minimal post-processing requirements. Material used in MJF are widely used in the automotive, industrial, consumer, and medical industry. Nearly 80% of the powder is reused. This is appealing to the industries as it can help reduce material waste, cost, and environmental impact. MJF parts are desirable for industry experts to design more safer and dependable parts that undergo different loading conditions due to their ductile fracture behavior. The high dimensional accuracy and surface finish shows the strength of the technology to be used to manufacture end product functional parts rather than just prototype parts. Thank you for your attention.